Okay, I've been asked to advertise the next AMSA general meeting, so there's information in the notes about that if you'd like to attend and check it out. So that'll be there for you. It's going to be, I guess, today at 6:30, so not a lot of advance notice, but that's happening if you want to go. Another thing before I start, as you might have noticed, for those of you that are here, the room is a little bit warm today. I've been warned about that there's some sort of temperature control problem, so if you're particularly susceptible to high temperatures, you have my blessing to skip class, although looking at the audience, it looks like most of you skip class without my blessing anyway. But for those of you that, if you have any issues with high temperatures, just be aware. It shouldn't get any worse than this. They have the doors open, they're working on the problem, but it's going to be warm in here today a little bit. All right, so as you guys know, the exam is going on now, but we're going to keep covering new material that will be not covered until the second exam, and also will be today we should finish everything that's going to show up on the homework assignment for this week. So today we're going to cover what's called molecular orbital theory, abbreviated as MO, so it's not pronounced MO, it's pronounced MO. MO theory is not really what I'm trying to say there. It's MO theory, which is molecular orbitals. So let's talk about before that, I forgot that it's Tuesday, so we're going to do this. What I wanted to look at today in terms of our sort of weekly reminder about work habits and things like that is, when are we actually doing our homework assignments? So we've talked about how many attempts you guys are all doing. Is right now it's averaging around 3 per student. I'd like to see that number at 4, but most of you are doing a good job with doing a good number of attempts on the homework. But then the question is, when are we doing it? So for the most recent homework assignment that was due this past Sunday, there were 365 total attempts out of 120 students, so just over 3 per student. But if we look at the distribution of when they're done, remember the homework assignments are open for 8 days, Sunday first thing in the morning until Sunday last thing at night. And so for those 8 days, in the first 7 days, there were 135 attempts done, and on the last day, there were 230 attempts done. So 63% of the attempts were completed on the last day, so a good number of you were waiting until Sunday to start. And if you look even more closely at that, 45% of all of these attempts were completed after 6 p.m. on the last day, so within the last 6 hours that the homework assignment was open. Now, I understand, I was a college student once, I understand the desire and sometimes the need to procrastinate. I'm not holding that against you, but I do think there are some advantages of doing homework assignment earlier in the week and kind of spreading out your attempts throughout the week, which I encourage you all to do. So the first thing is, if you do your homework attempts earlier throughout the week, you can start getting help from me or from your workshop leader or a tutor, whoever you sort of go to for assistance. You can get help on those difficult problems, and then on later attempts you can see if you really understand what's going on. If you save all your attempts till Sunday, it's too late. You have to just do them all, and if there's something you're not understanding, well then it's too late to figure that out and really practice it. I think spreading your attempts out also helps you avoid burnout. It doesn't take too long to do all 4 attempts on the same day. It's 2 or 3 hours, but at the same time, it's a lot of chemistry at once if you try to cram all those attempts right in at the last minute. So spreading that out, it'll be a little bit more clear and focused in your mind. And I just think in general, as I've tried to emphasize throughout this course, learning things and practicing things gradually day by day, the whole 1 hour per day guarantees that I have, if you do that, it's, I think, a better approach overall than sort of feast or famine, where you sort of cram in a bunch of chemistry on one day right before the assignment's due, and then you forget about it until the next week when the next assignment is due. So again, I always encourage you to spread out your effort in the course, sort of make it a day-by-day thing, and I think part of that would be by spreading out your homework attempts a little bit better than we are now. I mean, we typically finish covering all the material for that homework assignment no later than the Tuesday lecture, so you still have at least several days where you've covered everything already, and there's time for you to practice it throughout the week instead of waiting all the way till Sunday night, which at least half of you do. All right, so that's going to be my encouragement for this week. But now on to the new material. So if you'll recall, last time we covered what was called valence bond theory. So this is an idea, a model about covalent bonding that involves either atomic orbitals or hybrid orbitals on 2 atoms. So each atom has its own orbital, and those 2 orbitals overlap with each other to form a bond. And the electrons that are shared are sort of in that overlap region. And you have both sigma and pi bonds, and different atomic orbitals or different hybrid orbitals that can be involved in those. And that works very well for a lot of different compounds, and especially, as I've said before, if you go on to take organic chemistry, that valence bond approach, the idea about hybridization, that's going to be all over the place in organic chemistry, so you'll need to know it then. But it doesn't tell the whole story, unfortunately. Like any theory, it has its limitations, and we're going to talk about those today and talk about the more advanced bonding theory that takes care of all those limitations. So let's draw the Lewis structure of a simple molecule O2. So there's 12 valence electrons, and we would predict to satisfy the octet that we would get this Lewis structure. And we would then, from valence bond theory, say that this double bond is 1 sigma and 1 pi bond, where the sigma bond involves sp2 orbitals overlapping. If you count these as sp2 hybridized with 3 electron groups per oxygen, and then you have the unhybridized p orbitals. So that's what we would predict by just drawing a Lewis structure and then using valence bond theory to make some suggestions about how the bonding works. And from this Lewis structure, and from the way that valence bond theory works, we would predict that this molecule O2 has 0 unpaired electrons. Because remember, when we draw Lewis structures, we always pair up electrons. So we would have 2 electrons paired up in each bond, and then we have pairs of electrons that are arranged as the non-bonding electrons around each atom. And so we would say that none of the electrons in this molecule are unpaired based on this Lewis structure or based on how valence bond theory predicts the bonding will work in these. So what that means is, we haven't really talked about this yet, but what's the consequence of having paired or unpaired electrons? It determines what are called the magnetic properties of a molecule. And there's basically 2 limiting magnetic properties. So one of them is, if all of your electrons are paired, which is going to be true for almost every molecule we've talked about so far, if all of your electrons are paired, then the predicted magnetic properties are called diamagnetic. And what that means from a physical standpoint is that the molecule would be weakly repelled by a magnetic field. Diamagnetic molecules don't really have much of an interaction at all with magnetic fields, but if anything, they're weakly repelled. Okay, but there's not a strong interaction between a diamagnetic molecule and a magnetic field. So that's what we would predict for O2. It's diamagnetic, we put it in a magnetic field, not much of anything happens. But now let's watch a video to see what does happen when we put oxygen in a magnetic field, which I'm probably going to regret, because I think when I show videos is when I'm most likely to have my tablet freeze up on me. But anyway, we'll do it anyway. We'll try it, see, hope for the best. So what this experiment is going to involve, and I have the sound off, so I'll just narrate it myself. He's going to take liquid oxygen. So oxygen is normally a gas, as you guys know, you all breathe it in, but he's going to take really cold liquid oxygen and pour it between 2 strong magnets. And so let's see what happens. All right, so this is liquid oxygen, exceptionally cold, so obviously safety precautions necessary. And you can see that the liquid oxygen sticks between the 2 magnets. So it doesn't go through as we would expect if it's diamagnetic, but it's staying there in place. It's held by the magnetic field, it's attracted to the magnetic field. So that's what happens with O2, and you can see it's evaporating now because it's a very low boiling liquid, so at room temperature it'll evaporate very quickly, but as long as it's still liquid, it's going to stay in between the magnetic field. Okay, so that's what we see for O2, and I think there's some, I'll try to narrate their excitement there, so she's pretty excited about that. And then I think they also do nitrogen, right? Yes, so she prematurely ended the video, but he's going to do nitrogen instead. And so when we see with liquid nitrogen, you can see that it goes straight through. So she's pouring liquid nitrogen. So that's oxygen sticking to the magnets. And then I don't know if they'll do nitrogen again, but if you saw nitrogen, that's oxygen again. So they keep doing oxygen. But the one time they poured liquid nitrogen through, that one went straight through. So that one is what a diamagnetic substance would look like. Okay, but that's going to be what happens with oxygen. And so its predicted magnetic properties from valence bond theory are wrong. Again, valence bond theory predicts diamagnetic, but what we actually saw is that O2 is the other type of magnetic property, which is called paramagnetic. All right, so paramagnetic is when something is attracted to a magnetic field, and that only happens when you have unpaired electrons. So in reality, O2 has unpaired electrons, which we would never predict from valence bond theory. So what that means is, as often happens in chemistry, the theory is limited. It doesn't fully explain everything, so we need a more advanced theory to encompass that. And so what we're going to talk about then is the most advanced bonding theory we have, which is called molecular orbital theory. Now, molecular orbital theory is mathematically complicated, so we're really only going to talk about it for simple diatomic molecules primarily, so just 2 atoms bonded together. So we keep it simple in that way, but there's still some new things we need to learn and sort of try to understand the differences between, valence bond theory and molecular orbital theory, and then using molecular orbital theory to make predictions about some of the properties and some of the bonding arrangements in these small diatomic molecules. So what happens in molecular orbital theory is that you take atomic orbitals on each atom, and you're going to mix them together mathematically. So these wave functions, which again are mathematical functions, are going to be combined mathematically with each other. And the types of mathematical combinations we do are called linear combinations, which means we just either add or subtract two wave functions on the two different atoms. And what that forms are delocalized molecular orbitals. So the key distinction between valence bond theory that we talked about last time and molecular orbital theory that we're talking about today is that in valence bond theory you have an orbital on each atom and they're overlapping. And that area where they overlap is where the shared electrons are that form the bond. In this case what we're doing is we're taking orbitals in each atom and we're combining them mathematically to make a new orbital that belongs to the entire molecule. It's delocalized over the entire molecule. So basically two orbitals combined to make one whole delocalized molecular orbital. It's no longer two separate orbitals. So it may sound like a trivial difference, but it has some pretty significant effects then on some of the predictions we'll make as we'll get to. So it's a delocalized approach to bonding where we form new orbitals that belong to the entire molecule. We don't have atomic orbitals or hybrid orbitals anymore. We have new orbitals that are delocalized over the entire molecule. So what determines which orbitals can mix with each other? Are we going to just take every combination of atomic orbitals on one atom, every combination of atomic orbitals on another atom, and blend them together? Well, it's not quite like that. There are rules that sort of determine which orbitals can mix with each other. So the first thing is that only orbitals which are close in energy can mix with each other. So if two atomic orbitals are very far apart in energy, they're not going to be able to mix in this way to form molecular orbitals. So the molecular orbitals are going to be, again, linear combinations of atomic orbital wave functions, but the only atomic orbitals that are going to contribute to a molecular orbital are going to be ones that are pretty close in energy to begin with. And again, the important atomic orbitals, we're not going to consider every atomic orbital in the whole molecule, we're just going to consider the valence orbitals. Only orbitals which are close in energy can mix. All right, so if they're not close enough in energy, then they won't mix with each other in this way. But we still have to do a lot of mixing, and the ones that we're going to mix together are going to be valence orbitals. And we're going to talk about primarily, again, main group elements or main group compounds. So it's going to be s orbitals and p orbitals mixing together to make the molecular orbitals. That's how we're going to deal with this. All right, so when we mix orbitals together to make molecular orbitals, there are two types of molecular orbitals that can form. So one is called a bonding orbital and one is called an anti-bonding orbital. So when we mix two orbitals together, we get two molecular orbitals. We get two delocalized orbitals. One is going to be bonding, one is going to be anti-bonding. And so you still have a conservation of the number of orbitals you have. So if you have this many atomic orbitals to mix together, you're going to get that many molecular orbitals too. There's sort of a conservation of that number. And when you mix two different orbitals together, you're going to get bonding and anti-bonding pairs. So the bonding orbital wave function is a linear sum of two atomic orbitals. So an additive or in-phase combination of the two orbitals. And then an anti-bonding orbital, which will be abbreviated as psi star. So anytime you see a star next to an orbital, that means it's anti-bonding. And that's going to be an out-of-phase combination. So the same two atomic orbitals, but now subtracted from each other instead. All right, so that's how atomic orbitals combine. There's two possibilities. They combine in phase to make a bonding orbital, and they combine out of phase to make an anti-bonding orbital, and both of those will always happen whenever you mix two atomic orbitals together. Now, what's different between these two orbitals is going to be the electron density of them and the energy. So in a bonding orbital, the electron density is greater along the bond, or between the nuclei, if you want to think about it that way. So when you put electrons into a bonding molecular orbital, you have electron density between the nuclei that pulls the nuclei together. That's responsible for holding them together in that bond. That strengthens the bond whenever you put electrons into a bonding orbital. But then for anti-bonding orbitals, the electron density is greater outside of the nucleus, of the nuclei, I should say, for the two atoms that are bonded together. So that's going to be, instead of in between the two nuclei, outside of the two nuclei, that's where the electron density will be greatest. And in that case, when you put electrons into an antibonding orbital, you weaken the bond. So essentially, if the stronger the bond, you're going to have, the more electrons you have in bonding orbitals, the stronger the bond. But as you start putting electrons into antibonding orbitals, that will make the bond weaker. So that's kind of the difference between those two and their effects on the bond strength or the bond order. And that'll become more apparent as we look at the sort of mathematical aspects of this, which are pretty simple for bond order. And then the energy of the orbitals, again, in a qualitative sense, we're not going to be talking about the quantitative aspects of their energy. But a bonding orbital is going to be lower in energy than the atomic orbitals that are mixed together to make it. So you have two atomic orbitals at some energy. Usually the two atomic orbitals are the same energy because they're from the same atom, one on each side. And then the bonding orbital is going to be below those two atomic orbitals, and the antibonding orbital will be above. So the energy of the antibonding orbital is higher than the atomic orbitals, which I'll abbreviate as AO. All right, so that's how it works for bonding and antibonding. We mix two atomic orbitals together, we get one bonding, one antibonding. The bonding orbital is lower, antibonding orbital is higher. The average energy of those orbitals is going to be equal to the energy of the atomic orbitals. We still conserve energy. We're not gaining or losing energy by making these orbitals, but one's going to be lower, one's going to be higher. All right, so that's sort of the concepts. So then let's look at the shapes of atomic orbitals, and we're going to start with 1s orbitals. So we're going to take two 1s atomic orbitals. This is the simplest case we can have. So for example, H2, which has 1s orbital in each hydrogen, and we're going to mix them together to form delocalized molecular orbitals. So when we mix together two 1s orbitals, we get two molecular orbitals, one bonding, one antibonding, and they're both going to be sigma orbitals. So those things we learned last time, sigma and pi, the two different types of bonds we have, those are still relevant in molecular orbital theory. We still have sigma and pi bonds in this theory, just the orbitals that are involved look a little bit different. So a sigma orbital made from two 1s orbitals is going to be a sum of two 1s orbitals, and it's going to look like this. So we have the two nuclei, and then we're going to have a delocalized orbital that goes over the whole molecule, where most of the electron density is here in between the two nuclei. That holds them together in a bond. And then if we have an antibonding orbital, which we'll abbreviate as sigma star, indicating that it's antibonding, that's going to be an out-of-phase combination of two 1s orbitals. So we have a 1s orbital, and then on the other atom we have another one that's added out of phase, so we'll shade it in to indicate that that orbital is out of phase with the first one. And you have, in this case, a node in between the two nuclei with the electron density greatest outside of where the two nuclei are. So that's kind of what an antibonding orbital looks like. All right, and so again, if we add electrons to the bonding orbitals, that strengthens the bond because we're putting electrons between the nuclei. If we add electrons to the antibonding orbitals, that weakens the bond because we're putting electrons away from the nuclei, and they're not going to be held together as strongly. So what we're going to primarily concern ourselves with, though, are what are called molecular orbital diagrams. So understanding the mixing of orbitals, the ordering of the molecular orbitals, and then how to fill them with electrons to make predictions. So what it looks like for two 1s orbitals is we have, so on the outsides of the diagram, we're going to show the atomic orbitals that are mixing. So if we're mixing two 1s orbitals, two identical orbitals, they're going to be two orbitals at the same energy initially. And then we mix them together to make a bonding and an antibonding orbital. The bonding orbital is lower in energy. So the dashed lines just indicate that that orbital is a mixture of the two 1s orbitals. That's our bonding, sigma 1s. And then up here is our antibonding, sigma star 1s. All right, so again, two atomic orbitals mixed to give us a bonding and antibonding orbital. Again, energy increasing as we go up. All right, now the important part of the diagram is the middle part here. That's where we're showing the molecular orbitals. So a complete diagram, as we'll often show in this lecture, and you might see them on homework assignments, is going to indicate the atomic orbitals that are mixing and then the molecular orbitals that they form. The important part for making predictions about the molecule is going to be the ordering of the orbitals in this middle part of the diagram here. So that's the most important for you to sort of internalize and understand, is the order that these orbitals come in. So with two 1s orbitals, it's very simple. You have sigma 1s at the bottom, sigma 1s, star 1s at the top. And what you also see, which is going to be general for all the orbital diagrams we draw, is that the number of atomic orbitals we combine, in this case 2, is going to equal the number of molecular orbitals that we form. All right, I made that point already, but we're going to emphasize it here that however many atomic orbitals we mix, that's how many molecular orbitals we're going to get. Here it's 2 of each, two atomic orbitals mixing together to form 2 molecular orbitals. Okay, so then what we're going to be doing as we move forward is we're going to take this diagram, if we're talking about something that just has s valence orbitals like hydrogen, we'll take this diagram and we'll fill it with the appropriate number of electrons following Aufbau principle more or less, where you fill lowest energy to highest energy, and following Hund's rule where if you have degenerate orbitals, you put 1 of each before you pair them up. So those same rules for atomic orbitals will also apply to molecular orbitals, but we're going to get there in a second. But the things that you can then predict from the molecular orbital diagrams are really 3 things that we'll talk about once you have the diagram and once you put the correct number of electrons into it. So the first is the bond order. We've talked about bond order in the context of Lewis structures and valence bond theory. It's just how many bonds there are, is it single, double, or triple. But we can use the molecular orbital diagram to also predict the bond order, which usually matches up with what we would expect from a simple Lewis structure. Usually the bond order is not in conflict. Although another thing that molecular orbitals allow us to do, as we'll see, is we can predict fractional bond orders that are not whole numbers but are 1.5 or 2.5 or something like that. So you can have fractional bond orders from molecular orbital theory as well. And the equation for bond order is pretty simple. It's going to be 1/2 times the number of bonding electrons, so the number of electrons that are in bonding orbitals, minus the number of antibonding electrons. All right, and again, this sort of makes sense. As we put more electrons in a bonding orbitals, we increase the bond order, which means the bond is stronger. If we start putting electrons in antibonding orbitals, we subtract those because that decreases the bond order and makes it a weaker bond. And there's going to be, we can predict the bond types, so they're going to be sigma, pi, or some combination, where again, once we know which orbitals are populated, we can figure out if the net bonding that we have is sigma, pi, or some of each. And we can also predict the magnetic properties. This is kind of how we introduced why molecular orbital theory was needed and why it is, in some cases, important. So just to reiterate the magnetic properties, we have 2 possibilities, diamagnetic and paramagnetic. So diamagnetic means no unpaired electrons. And as we said, from a physical standpoint, that means it's going to be weakly repelled by a magnetic field. And then if it's paramagnetic, it's going to have 1 or more unpaired electrons. So there's really, again, just 2 classifications. It's a binary system here. And the physical property is that, as we saw for oxygen in that video, it's going to be attracted to a magnetic field. Okay, so that's other predictions we can make, which we haven't really talked about yet. You could do this also for atoms on the periodic table. If you predict the electron configuration of an atom, you can also predict if it's diamagnetic or paramagnetic, although we haven't seen that yet. But that's what we're going to do also for these molecular orbital diagrams. And so the other thing to keep in mind too is that if something has an odd number of valence electrons, like NO, nitrogen monoxide, that would have 11 valence electrons, that has to be paramagnetic. Anything with an odd number of valence electrons has to be paramagnetic because you can't pair up all the electrons if there's an odd number. But the nice thing about molecular orbital theory is that we can deal with systems that have odd numbers of electrons much more easily than we can by trying to draw a Lewis structure. Does that odd electron in a Lewis structure, does it go as a non-bonding electron? Is it shared between the 2 atoms as sort of a half bond? Well, that's hard to do with Lewis structures, but with molecular orbital diagrams, we can deal with that quite easily, as we'll see. So we're going to get to all that today, but these are the main things we're going to talk about in the context of this. So with that in mind, let's take the orbital diagram for H2 that we got and start filling it with electrons. Okay, so again, for H2, we have 1s valence orbitals that are shown on the outside of the diagram, and they mix to form sigma and sigma star molecular orbitals. That's as simple as it is. That's all you're going to see if you're talking about hydrogen or anything else that only uses s valence orbitals. Now let's just look for different molecules then that would use 1s atomic orbitals. So if we have H2 plus, so hydrogen but with a +1 charge, That's going to have one electron, because each hydrogen has one electron, but we take one away for the positive charge. So if we have H2+, that only electron is going to go into the lowest energy orbital. We always fill lowest energy to highest energy. And so that's what the diagram would look like for H2+. So if we predict the bond order then for H2+, remember that bond order is 1/2 times the number of bonding electrons. So we have for H2+, one electron, which is in a bonding orbital, minus the number of antibonding electrons. The antibonding orbital here is empty, so there's 0 antibonding electrons. And so we predict a bond order of 1/2 for H2+. So as I said, with molecular orbital theory, we can predict fractional bond orders, things that are not a bond order of 1, 2, 3, something in between in many cases. So here we get a bond order of 1/2, which indicates that we have one shared electron between the two hydrogen atoms in H2+. Yeah?
So when we get like numbers for each from 1 to 0.
Where do we get these numbers from, 1 and 0?
Yeah.
Okay, so this is the number of electrons in bonding orbitals. So bonding orbitals are the ones that are lower in energy and don't have a star next to them. So there's that one electron there. The anti-bonding ones are ones that are in orbitals that are labeled with a star, the higher energy ones.
Yeah.
And that one is empty right now, so there's 0 anti-bonding electrons. So total of 1 electron, it's in a bonding orbital, so it's going to be 1 minus 0.
Yeah.
So when you're doing these sort of bond order calculations, the two numbers you're subtracting are equal to however many total electrons you have. It's how many of them are in bonding orbitals minus how many of them are in anti-bonding orbitals. For any molecule you're dealing with, we'll see that's the case. If we go to H2, which we would predict from valence bond theory has a single bond, we'll see that molecular orbital theory makes the same prediction. So same orbital diagram, because it's still just 1s orbitals, sigma and sigma star. But this time for H2, we have 2 valence electrons, one from each hydrogen atom, and this time it's uncharged, so we keep both of them. And so when we fill these, we again fill them lowest to highest. Each orbital in molecular orbital theory can still hold 2 electrons, just like atomic orbitals. That's not different either. So both of them go into the sigma 1s. We always fill the lowest energy ones first before we put any electrons into the higher energy orbitals. So the bond order for this one is, again, 1/2 number of bonding electrons. This time both of our electrons are in the bonding orbital, so that's going to be a 2, still 0 in the antibonding orbital, and this time we get a bond order of 1, as we would have predicted if we just drew the Lewis structure of H2, the simplest Lewis structure we could imagine. Okay, so that prediction is held true. So you don't always get different predictions from molecular orbital theory and valence bond theory. In many cases, they line up with each other quite nicely, but molecular orbital theory is more complete and more correct, and in some cases where there is a discrepancy, molecular orbital theory will always be the one that works better. All right, any questions so far on these simple ones? All right, let's just finish the series then of the 1s diatomics. So if we have H2 minus, or additionally this could be He2 plus, either of those would have the same sort of number of electrons. This would be 3 electron system. So now we're adding an additional electron to H2, or we're starting with He2, which is 4, and taking one away. So either of these would have 3 electrons. And so in their molecular orbital diagram, still just 1s orbital, so they're going to make sigma and sigma star. When we add those 3 electrons, we put 2 in the lower energy orbital. Now the third one has to go up here. So we can again only have 2 electrons per orbital. So this is how they'd have to arrange themselves. In a bond order here, it's going to be 1/2, and then we have 2 bonding electrons, 2 in the sigma 1s. And then now we have 1 electron, that third electron that goes up here into sigma star, so we're going to subtract 1, and this is another one that has a bond order of 1/2. This time for a little bit different reason, because in this case, it's not that we're only sharing 1 electron, it's that we have our sigma orbital filled and our sigma star partially filled, so putting that 1 electron into sigma star, in some cases, it sort of partially cancels out the sigma bond. So we saw before with 2 sigma 1s electrons, you get a bond order of 1, but now the antibonding electron partially cancels out that bond, and it's down to a bond order of 1/2. All right, and then if we try to do He2, there's going to be 4 electrons in this diagram. Same diagram because it's still 1s orbitals. Now we're going to have to fill up everything, so you have 4 electrons total. So 1, 2, 3, 4, sigma and sigma star. And if we calculate the bond order for this, we have 2 electrons that are bonding in sigma 1s. The other 2 are anti-bonding in sigma star, and that comes out to a bond order of 0. So what does it mean when we predict a bond order of 0? What it means is that that molecule doesn't exist. It's not a stable molecule. There's no bond holding it together. So He2 is unstable, and it does not exist. Okay? So that's what we would have predicted for noble gases. Remember, noble gases don't typically make bonds with other atoms, especially with themselves. They like to just be by themselves. And so He2, this is sort of explaining why that is. You're filling the bonding and anti-bonding orbitals, so you have no net bond that holds the two together. All right? So any questions on the 1s case? Oh man, okay, a lot of them. Whoever wants to start, go ahead.
So if the 1s on the side, does it ever have electrons in them?
Well, so those are, what the orbitals on the side represent would be the individual atoms. So technically speaking, you could put electrons into them. Like you'd have one of them would have 2 electrons, one of them have 1 electron, each, an H and an H minus, for example. Or in this case for helium, each one has a 1s2 configuration. So those are showing the individual atoms before they're bonded together. So technically speaking, they could have electrons in them. You don't have to show them though. What we really care about is the middle part of the diagram. So I typically won't show them, but they could be there. Another question in the back?
Did you explain the 1/2 bond order?
So 1/2 bond order means in that the 2 atoms are sharing 1 electron. So in valence bond theory, we always talked about bonds as being 2 shared electrons. But in reality, you can have a single shared electron, and whenever you have a fractional bond order, that means one of the bonds is just a single shared electron in net. And so it means it's in between a 0 and a single bond. So it's not as strong as a single bond, but it's not 0 either like we got here. So it's in between those 2 cases. Anything else? You both had your hands up. Was that the same question? Okay, you guys are thinking alike and sitting together. That's cool. All right, so let's go on then to the more complicated diagrams that involve p orbitals. So we've dealt with the simplest case, which is just 2 s orbitals, whether it's 2 1s or 2 2s orbitals, whatever the case is, you're just going to get sigma and sigma star. But if we have p orbitals, we're going to have 2 types of molecular orbitals that can form. So what we're going to do is we're going to assume, these are all linear molecules, diatomic, so we're going to assume that the axis of the molecule is the x direction. Just so we keep it straight when we talk about the atomic orbitals that are formed. Because remember, for p orbitals, we have px, py, and pz. So we're going to define the x direction as the direction between the 2 atoms that are bonded together. In other contexts, you might see that defined as z, but not in this course, we're going to call it x. So if you take 2 px orbitals, those are going to be the 2 that are now facing each other between the nuclei. When you combine those, you're also going to make sigma and sigma star. All right, so your sigma p is going to be 2 p orbitals added together where they're going to overlap in between the 2 nuclei. So you have a px orbital on one atom, and I'll draw the nucleus in red. The nucleus is for p orbitals right at the middle of the 2 lobes, and they're going to be opposite phase. Now we're going to take a px orbital for another atom where, in this case, the phase that is the same, the 2 white phases as I've drawn here, the unshaded ones, those are going to be facing each other and they're going to overlap in between the 2 nuclei to make a bonding orbital. Okay, so that's how it's going to look, px and another px, and they're going to form a p molecular orbital that looks something like this. So you're going to have, again, it's delocalized over the whole molecule. It's not 2 separate orbitals anymore, but it's going to have constructive overlap in between the 2 nuclei, which are there and there, and then you're going to have the sort of other lobe that sort of shows up outside the nucleus. But again, you're going to have primarily electron density between the 2 nuclei that's responsible for bonding those 2 nuclei together. So that's what a sigma p molecular orbital looks like. All right, again, a delocalized orbital over the whole molecule, which now involves p orbitals instead of s orbitals, but it's still sigma because it's between the bond axis, between the 2 nuclei. Then if we have bonding, we also, as we said, have anti-bonding. So anytime we mix 2 orbitals together, you get bonding and anti-bonding. So this will be the subtractive combination of 2 px orbitals. So what does it mean when we subtract 2 p orbitals? What that means is that we're going to flip the sign of one of them, we're going to flip one of them over and combine it in an out of phase approach, where now what we're going to have is the two opposite phases are going to be lined up with each other, and what that results then is a molecular orbital that looks something like this. This is a little bit more difficult to draw, but we'll try. So you're going to have, in this case, between the two nuclei, an out of phase sort of alignment of those orbitals. All right, so again, that's nucleus there in red, and you're going to have a node in between the two because you have that out of phase overlap between the nuclear region. So most electron density, again, is outside the nuclei, so that's what we call an antibonding orbital. So this is your sigma star p. Usually 2p for the molecules we deal with, but any valence p orbitals can combine in this way, whether it's 2p, 3p, and so on. So that's sigma and sigma star for p orbitals, the ones that are aligned along the bond. But as we talked about in valence bond theory, you have two other p orbitals that are going to be perpendicular in this case to the bond, which we'll call py and pz. And so for those, they're going to be arranged in a pi symmetry, a pi fashion. So if we take two py atomic orbitals and add them together in phase, we'll get a pi bonding orbital. So that's going to be now an orbital that's perpendicular to the direction of the bond. Again, our nucleus in red is here and here. So the bond would be horizontal in this case, and now we're talking about two p orbitals that are arranged vertically, perpendicular to the bond. But those can overlap, again, above and below the bond to form a pi type of interaction. And in this case, we form a pi molecular orbital, which is going to be delocalized. So again, it's not two separate orbitals anymore. It's going to be the two nuclei, and they're going to have overlap above and below that nuclear region. Kind of looks like that. And they're going to be the opposite phase above and below, but again, constructive overlap above and below, making a delocalized pi p molecular orbital. So if we call this the y direction vertical, two py orbitals combine to form a pi p molecular orbital, where it's a delocalized orbital, but with constructive overlap between, but in this case, above where the bond is. And then if we form bonding orbitals, we still always have to form the antibonding counterpart, so the pi star orbital would be, in this case, if we're doing it with py, we take the subtractive combination. So when we subtract two p orbitals, again, that means we need to flip one of them, and they'll be combined in an out of phase. So that should be an additive combination. This is subtractive. And so what we end up with here is, again, two nuclei there. And then we're going to have sort of this type of shape, where they're going to be the opposite phases. In some sense, they're going to be repelling each other, and so we don't have constructive overlap anymore above and below the bond. It's going to be a sort of destructive or out of phase interaction, and that's going to be a pi star orbital. So I think it's helpful to know what the orbitals look like, just because, you know, it gives us a little bit of visualization of what's going on here. That's not going to be the most important thing we do, but what we have to recognize is that for p orbitals, you have these two possibilities. Sigma for the orbitals that are along the bond, pi for the orbitals that are perpendicular to the bond. And then we still have the pz that we haven't talked about. So this exact same pi interaction happens for pz. It's just going to be perpendicular to the page, so it's not going to be easy to draw. So our pz orbitals, which would be coming out towards you guys as I've drawn it here, those will also overlap in a pi and pi star manner to make those types of orbitals as well. So it would look exactly the same as this, just rotated 90 degrees out to facing you guys now. Okay, so that's the same thing. And so what happens then is that the pi orbitals are going to form degenerate sets. So you're going to get two degenerate pi p and two degenerate pi star p orbitals. So at those energy levels, you're going to have two orbitals at the same energy, pi p and pi star. All right, so again, we'll see that in the diagrams that we'll draw more clearly. But you're going to get a set of degenerate orbitals. So when you mix p orbitals together, you get either sigma and sigma star for the two that are aligned along the axis, or you get a set of 2 pi and a set of 2 pi star orbitals for those pi ones that are perpendicular to the axis. And again, you're going to get 2 of each pi orbital, 2 pi and 2 pi star, and those are going to be degenerate at the bonding level and degenerate again at the anti-bonding level. Degenerate meaning same energy. So let's look at what the diagrams look like then. So we're going to start with the second half of the p block. So we're going to do this for all the 2p elements. And it turns out there's slight differences in the orbital diagram depending on which p group elements you're dealing with. So we're going to have to cover that and you know, the consequences of that a little bit later. But for these 3 elements that are the second half of the p block, group 6, group 7, group 8, they're all going to follow this basic diagram here, which I'll fill in and label now. And so what happens in these atoms here is they're going to have now 2s and 2p valence orbitals. All right, because remember the valence electrons for the p block are the s and p electrons that are in the outer shell. So we have to count the 2s and the 2p, and we're going to draw orbital diagrams that involve those. So each atom, again, the atoms individually are shown on the outside of the diagram. Each atom is going to have 4 atomic orbitals that we're mixing, so that's a total of 8, and so we're going to form 8 molecular orbitals that are all shown here in the middle of the diagram. So let's look at how they're labeled and the order that they come in. All right, so the ones that are lowest in energy, remember 2s orbitals are lower in energy than 2p. They're filled first in the periodic table, so that's why they're shown at the bottom. And just like before, when we mix s orbitals, we get sigma and sigma star. So for a molecular orbital diagram that involves 2p elements, or any element from the p block, your bottom part of the diagram is going to look just like this, like we talked about before, mixing a 2s orbital and make a sigma and a sigma star. But now the part of the orbital diagram that involves 2p is going to be a little bit more complicated, because now, as we said, you can make sigma or pi bonds. Now let's talk about the relative ordering of the energy of those a little bit. Something we haven't talked about yet, but is still fairly important, is that how much the energy of the orbitals split, you know, how much does the bonding orbital go down, how much does the anti-binding orbital go up, that's determined by how strong the overlap is between those 2 orbitals. So if you think about it, we've talked about this maybe a little bit before, but not in these exact terms. If you have a sigma overlap, which is head-to-head overlap between the 2 nuclei, that's a very strong direct overlap between the 2 orbitals, and so that means those energy levels are going to split to a larger amount. Whereas for the pi interactions, which are sort of, again, perpendicular to the bond, it's above and below, it's not as direct of an overlap, and so those orbital levels are going to split by a smaller amount. So when we look at the ordering of these orbitals here, our 2p orbitals, the ones that form the sigma interactions, that's going to be stabilized the most from the atomic orbital, because that's the strongest overlap. And similarly, the anti-bonding sigma star, 2p, is going to be the highest energy. You're going to get the biggest splitting in energy because those sigma interactions are the strongest, so that causes the bonding orbital to go down the most and the anti-bonding orbital to go up the most. So that's why those are shown in that way. And then the pi interactions are weaker, so you'll still get the bonding orbital lower in energy, but not by as much, and the anti-bonding orbital higher in energy, but also not by as much. So that's the order they come in. And again, remember at the pi levels, we have 2 degenerate orbitals at each level. One from py, one from pz, in those 2 different directions, but same energy. So you have degenerate orbitals now that we have to worry about. So let's go ahead then and fill this diagram for oxygen. So we have to think about how many valence electrons does O2 have. Each oxygen has 6 valence electrons. It's a group 6 element. So we're going to get 12 valence electrons for O2 that we need to then put in this diagram here. So we're going to fill it bottom to top, is lowest energy to highest energy. We're going to follow that principle. We're going to follow Hund's rule as well. So we go 1, 2, 3, 4, 5, 6. Now when we get to the degenerate levels, we go 7, 8, one at a time, 9, 10, then we pair them up. So now when we get up here to these, we have 2 electrons left, that's 10, we have 2 more to put in. We're going to go 11, 12 up there, 1 in each orbital. Remember, for Hund's rule, we still follow that. If you have degenerate orbitals, you fill them 1 at a time before you pair up the electrons. Okay, so that's what O2 is going to look like. And so what we can see now is that in this diagram up here, O2 has 2 unpaired electrons, which means it would be predicted to be paramagnetic. That matches up the observation that we talked about at the beginning of today. All right, so this is one of the crowning achievements of molecular orbital theory, is that it does correctly predict the magnetic properties of O2 and other molecules that are not so easy to predict using valence bond theory or just simple Lewis structures. And this is observed experimentally. All right, so whenever your theory sort of matches up with experiment, that means you're on the right track. All right, and that's exciting to us as chemists, so I will use a rare exclamation point there to indicate that. All right, so whenever that happens, that means that your theory is an improvement over what we had before, because valence bond theory, we thought that O2 would be diamagnetic. with molecular orbital theory, we correctly predict that it's paramagnetic with 2 unpaired electrons, okay? And that's because, again, those last 2 electrons go into a degenerate set of orbitals where we put 1 electron into each orbital to follow Hund's rule. And if we calculate the bond order for O2 using this diagram, we have a total of 12 electrons. We have to figure out how many of them are in bonding orbitals and how many of them are in antibonding orbitals, and then subtract the 2. So remember, the bonding orbitals are the ones that are lower in energy and are not labeled with a star. So we have these 2 electrons that are in the bonding orbital, and then 4, 6, 8. So 8 of our 12 electrons are in bonding orbitals, 2 in sigma 2s, 2 in sigma 2p, 4 in pi 2p for a total of 8. And that means the other 4 should all be in antibonding orbitals. So we have 2 electrons in sigma star 2s, that's 2, and then 2 more up here in pi star, so a total of 4 electrons that are in antibonding orbitals. So remember, the 2 numbers that you subtract equal the total number of valence electrons you have, bonding minus antibonding. And so we get a bond order of 2 for oxygen. That's also what we would predict from valence bond theory. So typically the bond order doesn't differ from what you would draw from a Lewis structure, but the magnetic properties in this case were predicted correctly, unlike the case with just the Lewis structure or valence bond theory. All right, so any questions on that diagram or those concepts? Okay, so the next thing we need to deal with is, let's just do one more element at least. I guess we're going to do all of them just to be complete. So this will be a little bit repetitive, but just again, get practice with this. So for F2, it's going to follow the same diagram. 2s and 2p valence orbitals. The s orbitals mix to make a sigma and a sigma star. And then the p orbitals mix to make a sigma and a pi at the bottom, degenerate pi, and then a degenerate pi star, and a degenerate sigma star. So at minimum, when you're learning molecular orbital theory, make sure you know the ordering of the orbitals in the center part of the diagram here. You know, the sigma and the sigma star 2s at the bottom, and then the order that these orbitals come in, because that's the order you need to populate the electrons whenever you're asking a question about bond order or magnetism or whatever else we decide. All right, so for F2 now, we're going to put 14 electrons into this diagram. It's 2 group 7 elements now, so 14 total. And so we're going to get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So in this case, we completely fill the pi star 2p with those 2 extra electrons that we have for fluorine compared to oxygen. So we would predict that this is diamagnetic, which indeed it is. So F2 is a diamagnetic molecule, and its bond order, we have still 8 electrons in bonding orbitals. That's the most we can have. If we fill all of our bonding orbitals, that's 2, 4, 6, 8 electrons in bonding orbitals. But this time we have 6 electrons that are antibonding, 2 from sigma star 2s, 4 more from pi star 2p, so 6 antibonding. So we get a bond order of 1. And then the other thing you might have to do in homework assignments, at least in a multiple choice sense, is sort of identify the electron configuration for the molecule. So we wrote electron configurations for atoms, you know, 1s2, 2s2, whatever. We can do the same thing for molecules using these molecular orbital labels as well. So this one will be written as, we write it from, you know, lowest to highest, sigma 2s2, sigma star 2s, 2, sigma 2p2, that's the number of electrons in each of those orbitals. Pi 2p 4 and pi star 2p 4 as well. So that's how many electrons, 2, 2, 2, 4, 4 are in each of these orbital levels that we go through. And then sigma star 2p is empty, so we don't have to include that in the configuration. That would have 0 electrons in it. So you may also be asked to just present the electron configuration, so it's written the same way as it was for atomic configurations. Just list each orbital level and then how many electrons are in each of those. So that's how it would look for this one. All right, and then the last 2p element is neon. Now we would predict, based on the properties of noble gases, that neon does not form a diatomic molecule with itself. Remember, noble gases are also called inert gases. They don't tend to form bonds with much of anything, especially with each other. So we wouldn't predict this molecule to exist, but let's see what happens when we draw its orbital diagram. So now we have to put in 16 valence electrons, same valence orbitals, 2s and 2p. Same molecular orbitals that form from that overlap. So again, knowing this order is going to be key. And now we have to fill these with 16 valence electrons. So when we do that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We filled every orbital in the diagram. And when we calculate the bond order, as you might already imagine just by looking at it, all the antibonding orbitals are filled and all the bonding orbitals are filled. So our net bond order we have is going to be 8 bonding electrons. All the bonding orbitals are filled with 8 electrons. But then we also have 8 antibonding electrons. Sigma star 2s and the pi star and sigma star 2p are all filled with a total of 8 electrons. So remember what it means when we predict a bond order of 0, that means this is an unstable molecule, it doesn't exist. All right? So we know from the properties of noble gases that any 2 shouldn't exist, and the molecular orbital diagram also predicts that because you get a bond order of 0, which essentially means it's not a real molecule, it doesn't exist. Okay. Any questions so far on those? Because that's going to be sort of the slightly more straightforward case for 2p elements. Yeah.
So for the diamagnetic and the paramagnetic, how do you figure that out from looking at the pi 2p?
So that's going to be determined by whether or not there are unpaired electrons. So remember, an unpaired electron is one that would be spin up typically without a spin down electron next to it. So in this diagram here, you have 2 singly filled orbitals that each have 1 spin-up electron. So there's 2 unpaired electrons. One.
So you would just look at the individual orbital by itself to see whether it has a
Yes. So the only things that are going to be paramagnetic are ones that either have an odd number of electrons overall. They have to be paramagnetic because you can't pair up all the electrons. Or in this case, it's an even number of electrons, but you have a partially filled set of degenerate orbitals like we do here. So anytime they're partially filled degenerate orbitals where you don't have spin down electrons paired up with each spin up electron, that would be a situation where it's going to be paramagnetic. So you can't really easily just look at the electron configuration necessarily. You have to sort of, again, keep in mind the degeneracy of the pi orbitals and figure out whether they're singly filled or doubly filled to figure out if it's paramagnetic or not. So that's where the actual diagram becomes more helpful. Anything else on that? All right, so now let's go on to the first half of the P block. So group, what was that, 3, 4, and 5, boron, carbon, nitrogen, if we're in the 2p block, and look at a slight difference in the diagram. Now in terms of predicting the bond order, this difference doesn't matter, but in terms of predicting the magnetic properties or the types of bonds that you have, this is actually fairly important. So if you look at the orbital diagram for this part of the periodic table, it's the same valence orbitals, 2s and 2p, but this time there's something a little bit different. So the 2s looks the same, sigma and sigma star, no big deal. But then when we get to the 2p levels, what happens is that the pi bonding orbital comes lower than the sigma. So those two switch. That's the only difference, is that these 2 orbitals from the 2p level, they switch. Instead of sigma at the bottom and then pi, it becomes pi at the bottom and then sigma. The top 2 are the same. So that's the only part of the diagram that's different, is those 2 orbitals there. All right, so we'll sort of highlight that. These 2 switch. For the first half of the P block, B2, C2, and N2, which is, again, anything that has a P1 through a P3 valence configuration. Okay? So for those 3 elements of the first half of the P block, these 2 are in a different order. And that's a little bit counterintuitive, right? Because we talked about how the splitting of the orbitals is determined by how strong the interaction is between the 2. And so why would a pi orbital come below a sigma? It's kind of a complicated reason that we don't really expect you to fully know or understand. But it's not quite as simple as, 2s mixes with 2s, 2p mixes with 2p. In reality, s and p orbitals can also mix with each other if they're both sigma. So we have sigma orbitals at each level, and so there's actually more complicated mixing where the 2p orbital mixes in a little bit to these 2s orbitals. These 2s orbitals mix in a little bit with those 2p orbitals, and that pushes the energy of the sigma 2p up a little bit. And the reason that happens for these elements and not for the other 3 is because in these elements, the 2s and the 2p orbitals are closer together in energy. So when the orbitals are closer together in energy, they can mix more effectively. So again, we don't expect you to really know why that is, but there is a reason. It's not random, and it's because of mixing between these sigma 2s and sigma 2p orbitals that drives the energy of this sigma 2p orbital up a little bit from where it normally would be if there was no mixing. Okay, so that's the reason, but you have to remember that, especially if you're asking about magnetism or bond properties. So if we do it for B2, which has 6 valence electrons, I mean, I challenge you to try to draw a Lewis structure of B2. You're gonna, fumble all over the page just like I would. So there's not really an easy way to draw a Lewis structure of this, but if we use the molecular orbital theory, we can predict the bond order, what type of bond it is, and the unpaired electrons all very easily. So for 6 valence electrons, we're gonna go 1, 2, 3, 4, and then we have to again do singly filled pi orbitals, 5, 6 in this case, like that. Okay, so we predict that B2 is paramagnetic. Now this is not like a particularly stable or well-known molecule, but it can be observed and it's paramagnetic. And then if we predict the bond order, it's going to be 1/2, and then we have 4 of our 6 electrons are in bonding orbitals, 2 from the sigma 2s, 2 from the pi 2p, those are both bonding orbitals, so they have 4 electrons total. And then our sigma star 2s is always typically going to be filled, so that's going to be our 2 antibonding electrons. So we get a bond order of 1 for this, with an electron configuration of sigma 2s2, sigma star 2s2, and then pi 2p2. So each of these energy levels has 2 electrons in it for a total of 6. Now what's weird about this one, which we would never predict from valence bond theory, is that this is a single bond. And we said in valence bond theory, we assume that all single bonds are sigma, but actually this bond here is a pi bond because sigma and sigma star 2s are both filled, so those sigma interactions cancel each other out, but then we have 2 remaining electrons in a pi orbital. So the net bond in this case is actually a pi bond. So this is another prediction that we would never get from valence bond theory, but can sometimes happen. We get a single bond, but instead of being sigma, it's a pi bond. All right? So that's what we would predict here. We're not going to go into this in too much detail, predicting the type of bond, but it's pretty easy to do because we see, again, sigma and sigma star are filled, so there's no net sigma bond. The only net bond that we have is the 2 electrons in the pi orbital, so our 1 net bond is actually a pi bond, not a sigma. All right, so that's how it would work for B2. Let's go on to the other members of that first part, so C2 and N2. C2 has 8 electrons, again, not something that would be easily drawn as a Lewis structure, but we're going to have the same orbital diagram. And again, because it's in the first half of the p block, we're going to have pi 2p coming below sigma. All right, so that's going to be the order, same order as before, but now we just have 8 electrons instead of, and I forgot to label these, that should be sigma and sigma star. And so now we have to put our 8 electrons in, so it's going to go 1, 2, 3, 4, 5, 6, 7, 8. So just 2 more electrons that are now going to pair up in those pi orbitals. This molecule is predicted to be diamagnetic, because in this case, all of the orbitals are doubly filled with 1 spin up and 1 spin down electron. The electron configuration is sigma 2s2, sigma star 2s2, pi 2p4 this time. And the bond order, if we predict that, so from the electron configuration, we see that we have 2 plus 4 is 6 electrons that are in bonding orbitals. We still have the 2 sigma star 2s that are anti-bonding. So this comes out to a bond order of 2 or a double bond. And again, it's a little bit different of a double bond than we would predict from valence bond theory. In valence bond theory, if we have a double bond, we say that it's 1 sigma bond and 1 pi bond. But in this case, it's a double bond, but there's no sigma interaction, only pi. So it's going to be 0 sigma bonds, in this case 2 pi bonds to make the double bond. Again, different than what we would predict from valence bond theory, because here the sigma and the sigma star are both filled, and the lowest energy bonding orbital that is filled without the anti-bonding orbitals also being filled is pi. So we have 2 pi bonds, 2 filled pi orbitals, makes 2 pi bonds for a double bond. Not something we would predict from drawing a Lewis structure using valence bond theory. All right, that's C2. And then finally, one that we know is a stable molecule, N2, because it makes up about almost 80% of our atmosphere. Nitrogen is everywhere. Let's make some predictions about that. So nitrogen is 10 valence electrons, 2 group 5 elements for a total of 10. And because it's in the first half of the p block, it's going to follow this first order, this alternative order here, where the pi 2p comes below sigma. So I always forget to label those. Sigma and sigma star, pi, sigma, pi star, sigma star. So again, it's only these 2 orbitals that switch depending on whether you're talking about boron, carbon, nitrogen versus oxygen, fluorine, neon, first half versus second half of the p block. So we have 10 valence electrons for N2, so they're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so all the bonding 2p orbitals are filled. So we predict N2 to be diamagnetic, and if you remember from the video, it was. So N2 went right through the magnetic field as any diamagnetic substance would. So that prediction is correct, and we'd also get that from the Lewis structure. The bond order in this case is we have 8 electrons are in bonding orbitals. All of our bonding orbitals are filled. Sigma 2s, pi 2p, sigma 2p, a total of 8 electrons in bonding orbitals, and only these 2 in the sigma star are antibonding. So we predict a bond order of 3 or a triple bond. Triple bond order is the highest you can get for these p block elements drawing either their Lewis structure or their orbital diagram. We'll never see a bond order greater than 3. And the electron configuration is sigma 2s2, sigma star 2s2, and then pi 2p4, sigma 2p2. So actually there's nothing weird about the predictions for this molecule that you would get from molecular orbital theory. It's a triple bond. That's exactly what we would get if we drew nitrogen Lewis structure as a triple bond to satisfy the octet rule. It's diamagnetic. That matches up both with the Lewis structure and with the experimental properties that we saw in the video. And we fill the pi and the sigma orbitals, so it's a triple bond with 1 sigma and 2 pi bonds. So that's also what we would predict from valence bond theory. So N2 is one of those cases where there's no real differences between the predictions you would make from valence bond theory and MO theory. But as we saw in many cases, there are differences, or there are some molecules that are hard to deal with by just drawing a Lewis structure. And so the molecular orbital theory is a much more powerful way of dealing with those ones and much more complete. Okay, any questions on that? All right, the last thing that I'll show for these diagrams is what we can still have fractional bond orders as well. So this is called, I believe it's called the diazonium cation. So it's N2 with a positive charge. So we saw N2 in the last example had 10 electrons, and now we're going to have 1 fewer electron because of the positive charge, so this will be 9. And as we said before, dealing with odd numbers of electrons in a Lewis structure can be challenging. What do we do with that odd electron? Do we leave it as a non-bonding electron? Do we try to share it between the 2 atoms as a half bond? And again, with molecular orbital theory, we just populate the orbitals exactly as we would before, and we just have to make sure we're using the correct number and have the orbitals in the correct order. So this kind, because again it's nitrogen, we're going to go with this order here where the pi 2p comes below sigma. And then pi star and sigma star at the top. Okay, so that's going to be our diagram, but this time only 9 electrons go in. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9. So our sigma 2p is now only half filled with just a single electron. We already know this is paramagnetic because it has an odd number of electrons. So, I don't like this term, but I'll say it anyway. Pro tip, if you're doing a homework problem and you see one that has an odd number of electrons, you automatically know this is paramagnetic. So you don't even have to draw the orbital diagram if that's all you're asked about it. But if we could ask other things too where you need the diagram to help you. So for example, the bond order, you're not going to easily get the bond order just by looking at this molecule or trying to draw it out. So we can predict the bond order for this one from the electron configuration. So the configuration would be sigma 2s2, sigma star 2s2, pi 2p. That pi looked weird. I think my pen might be about to flake out, so let's hope we can get to the end of this with it before that happens. Pi 2p4, and then sigma 2p is now just singly filled, as we said. So that's the electron configuration. That's where our 9 electrons go. And then if we predict the bond order for this, anytime you have an odd number of electrons, you're also going to have a half fractional bond order, something that's not an even number, but either something 0.5. So in this case, what we get is We have 7 electrons that are in bonding orbitals, these 2, and then these 5 up here, so 2, 4, 6, 7. And we're pretty much always going to have the 2 sigma star electrons that are going to be anti-bonding, at least, and so that's going to be what we have for that. So we get a bond order of 2.5. So compared to nitrogen, which is a bond order of 3, N2 plus, which has 1 fewer electron, is a bond order of 2.5. And this also sort of helps us, another sort of key concept, which I think is apparent, but we should state it up front anyway, is there's sort of 2 ways to reduce the bond order. You can either remove electrons from a bonding orbital, that's what we did here. So nitrogen was a bond order of 3 and this orbital was filled. We take 1 electron out and now the bond order goes down by 0.5. Or alternatively, if we had N2 minus, where we put 1 extra electron into the anti-bonding orbital, that would also reduce the bond order to 2.5. So there's 2 ways of reducing the bond order. You either take an electron out of bonding orbital like we did here, or you start adding electrons to anti-bonding orbitals. Those are the 2 main ways you can reduce the bond order of something. And so this is, this is an example of that, where we moved an electron and reduced the bond order. All right, so any last questions on those sort of diatomic molecular orbital diagrams? That's basically 99% of what you'll have to do for the homework questions that you'll see on this topic is, know how to draw the diagrams, know how to figure out how many electrons there are, and predict some of those properties like magnetism, bond order, stuff like that. So any questions on that? Okay, the last thing we're going to cover today before we get out of this sauna is going to be a little bit about delocalization and molecular orbital theory. So it gets a lot more complicated to talk about things that are not just diatomic linear molecules. If you take the other course that I teach, which is a graduate level course, which I'm guessing most of you won't get to before you graduate, which is a shame. But if you did, we talk about molecular orbital theory in that class for all kinds of things. It's a lot of fun. But for this class, again, linear molecules are the ones that are the most straightforward to deal with, and that's mostly what we're going to do. But there is one thing that the book covers, which is fairly interesting, about using molecular orbital theory to understand delocalization in a larger molecule. So remember, the key idea about molecular orbital theory is that the electrons are delocalized over the whole molecule in orbitals that now are belonging to that whole molecule, not individual atomic orbitals anymore, but delocalized molecular orbitals. And we can do that for a fairly interesting molecule called benzene and understand how that delocalization works a little bit. All right, so benzene is an organic molecule with the formula C6H6. There'd be no easy way for you to predict the structure at this point in your chemistry career, but what it looks like is it's a hexagon of carbon atoms. And I'm not used to drawing it this way. There's a shorthand method that you'll learn in organic chemistry, but I don't want to confuse you with that. So it's a hexagon of carbon atoms. Each carbon has 1 hydrogen bonded to it. And if the name benzene sounds familiar, that's because 2 or 3 years ago in Houston, this molecule was in the news because there was a big fire. I think it was a Shell oil facility somewhere in I don't know where, the Pasadena or Deer Park area down there. And they were releasing a bunch of benzene into the air, and a lot of people freaked out because benzene is pretty carcinogenic. Luckily, it was managed pretty quickly, so there wasn't a huge environmental cost to that. But benzene is a pretty, toxic, but also a pretty useful molecule, so you might have seen it in the news. Now, this molecule here, as I've drawn it, C6H6, right now, each carbon only has 3 bonds. As we talked about, carbon wants to have 4 bonds in a typical Lewis structure to have a complete octet. So we need to have alternating single and double bonds in this hexagon here. Okay, so you have alternating single and double bonds. Every other bond in this hexagon is a double bond and a single bond. But then there's going to be 2 resonance structures you can draw. So I put the double bonds here, here, and here. But there's an equivalent structure where the double bonds are in the alternate position. So we have to draw the same hexagon again. With terminated by hydrogen in each spot. This is a totally flat molecule. I'm drawing it as a hexagon, and that's indeed what its shape is. But now we can also draw the alternative structure where the double bonds are here, here, and here. So there's 2 equivalent resonance forms. And again, what that indicates to us is not that we have, it's sometimes a double bond, sometimes it's a single bond. What we have is a blended structure where the real structure is the combination of these 2, where these pi bonds, these the ones that make the double bond, the pi bond, are going to be delocalized over the whole ring at the same time. So another way that you might see benzene drawn is like this, where you have your hexagon. I didn't leave myself enough room, hang on. Yeah, go away. Come on. It's not gonna let me get rid of that carbon. That's annoying. But anyway, another way to draw benzene, there's a hydrogen down there that I ran out of room, and that's a hydrogen, not a carbon. It's like this, and then you draw sort of a circle in the middle to indicate that you have those delocalized pi bonds. They're not, it's not that it's here or here, it's that it's really the pi bonds are circulating around the whole ring. So we have all identical bond lengths, so it's not, again, single alternating with double, it's equal bonds that are in between a single and a double. So we'll draw that as a C with a single bond and then a dash. And if we predict the hybridization of all these carbon atoms, each carbon atom in the structure, whether you look at the resonance structures or the one down here, each carbon atom is bonded to three things, 2 carbons and a hydrogen. So when you have 3 things bonded to an atom, what's the hybridization going to be? All carbons are going to be, there's 3 things, so it's going to be sp2 hybridized. They hybridize 3 orbitals. Okay, so we have sp2 hybridization at each carbon atom. And when we have sp2 hybridization, remember that you leave one of the p orbitals, because there's a total of 3 p orbitals on each carbon. One of those is going to be an unhybridized orbital that's going to be perpendicular to the plane of that hexagon. So when we describe the bonding in benzene, we can actually, in a very convenient way, do it with sort of a combination of valence bond theory and molecular orbital theory. So it's not necessarily that one theory is always better than the other. It's that sometimes one is more convenient, sometimes another one is more convenient. And describing the sigma bonds in benzene is actually done more conveniently with valence bond theory. So as we said, each carbon atom is sp2 hybridized. So what you have at each carbon atom is going to be 3 identical sp2 orbitals that are arranged in a trigonal planar fashion. So that's one carbon atom there. And you have your other carbon atom, which has, this is challenging my artistic abilities really, so I'm probably going to screw this up, but I'll try. All right, so they have another carbon atom there, and then another carbon atom there. So each carbon atom has a set of identical sp2 orbitals that are arranged in a trigonal planar fashion. I'm not doing a great job of drawing all those angles correctly, but hopefully you get the idea. So each carbon atom and then another carbon atom there. And then the 6th one there. And I kind of did it right first time. Not perfect, but hopefully you get the idea. Oh gosh, that's a terrible looking hexagon. But anyway, imagine that's a hexagon, and each carbon atom, I'll highlight C in red, that's where each carbon atom is, has sp2 hybrid orbitals, and they're going to overlap around this hexagon to make all of our sigma bonds between the carbons. And then they're also going to overlap with a 1s orbital from hydrogen to make the sigma bonds to hydrogen that are outside the ring. All right, so again, valence bond theory says we have sort of these localized orbitals on each atom, and so you're going to get sp2 orbitals on carbon overlapping around the ring, and then one outside the ring that overlaps with hydrogen to make the sigma bonds. So these are all of the sigma bonds. So the sigma bonds are going to form by overlapping sp2 orbitals on carbon, or you can have sp2 orbitals overlapping with 1s orbitals to make the CH bonds that are outside the ring. All right, so valence bond theory can sort of conveniently and in a nice way describe the sigma bonding in this ring, where it's hybrid orbitals all around, and you get overlap of those hybrid orbitals to make the bonds in the ring between the carbon atoms and the bonds outside the ring with the hydrogen atoms. But valence bond theory is not as convenient for describing the pi bonding in this molecule, because as we said, the pi bonding in this molecule is delocalized over the whole ring. It's not that you have a pi bond between these 2 carbon atoms and a pi bond between these 2. It's really a set of 3 pi bonds that go around the whole ring, and there's not a good way to do that with valence bond theory, because valence bond theory, again, is a very localized approach that would presume that you just have 2 overlapping orbitals next to each other. So the way that we can describe the pi bonding in benzene is with a delocalized molecular orbital approach. Now, we're not going to talk about the details of these molecular orbitals, but imagine you again, what you have is this sort of hexagon here, which I'm trying to draw sort of on its side. And so remember, each point in this hexagon is a carbon atom. So there's going to be carbon there, a carbon there, a carbon there, a carbon there, a carbon there, and a carbon there. The carbons are sp2 hybridized, as we just said. And when you have sp2 hybridization, that leaves one unhybridized p orbital. So at each carbon atom, you're going to have a p orbital that's perpendicular to the ring. And what you can do to make the pi bonds is you have all the phases lined up above the ring and all the phases lined up below the ring. And so you get this sort of delocalized overlap of all 6 of these orbitals above and below the ring. So again, valence bond theory assumes that you can only have overlap involving 2 orbitals at a time that are right next to each other. But with molecular orbital theory, if we put a p orbital on each carbon atom, we can draw delocalized molecular orbitals that look kind of like this, where the electron density is delocalized over the entire molecule, and that again explains then that delocalized pi bonding that we have in this structure. So that's as much detail as we're going to go into that. Again, it's not going to be a huge point of emphasis. You just might see something on the homework, so I don't want you to be confused about that. But you have these delocalized pi molecular orbitals, and they're formed by overlap of unhybridized p orbitals. And we'll call them the 2pz orbitals, being perpendicular to the xy plane of the hexagonal molecule. So you can use, again, valence bond theory to describe the sigma bonds, molecular orbital theory with delocalized molecular orbitals involving all 6 pi bonds, all 6 pi orbitals to make these delocalized pi bonds. And it's more complicated than that, but that kind of gets at the essences of what's happening with this delocalized approach. All right, so any last questions before I wrap up today? All right, thank you for coming. Good luck on your exam if you haven't taken it yet, and I'll see you guys on Thursday. And oh, by the way, office hours today, pretty much now until 2:30, and then about 3:30 to 5 I should be there. So if you need to stop by, I'm a little bit flexible, so don't worry about coming any of those times. Just there'll be about an hour in the middle of the afternoon that I can't be there. But other than that, I'll be around. I'm just going to stop.